All right, so welcome everyone to the to Rutgers ECE Colloquium, and also at the same time to the Shannon channel. So I'm really excited today to have Michael Gaspar from EPFL to give a talk today on common information component analysis. So a brief introduction to Michael. So Michael is a professor at EPFL in Switzerland, and before that he's a professor at UC Berkeley. And he earned his PhD from EPFL also in Switzerland. So Michael's research interests are in general in network information theory and related coding and signal processing techniques with a focus on application to sensor networks and neuroscience. And also he's a fellow of the IEEE. He's a co-recipient of the 2013 Communication Society and Information Society Joint Paper Award. And he was an Information Theory Society Distinguished Lecturer. And he won many prestigious awards, including the ERC Starting Grant and the NSF Career Award. Michael, we're very excited to have you here, and the Zoom floor is yours now if you want to start.
Whoops, that was a nice feedback. Thanks very much, Salim, for the kind introduction and of course for the invitation. Yeah, I have to say actually for these types of seminars, it's the very first one I'm giving. I've done conferences, but not this, so I don't know, we'll see. At the same time, it's also the very first time that I'm giving a long talk about this topic, so I'm sure there's plenty of stuff that's not intelligible. And yeah, I should encourage you to interrupt me with questions. I may not be able to monitor the chat, so if you have an urgent question, you can put it on the chat and then Salim can interrupt me. Or else you can just, well, I don't know, unmute.
Maybe wait until the end.
So, or wait until the end, exactly. So, good. So yeah, it's a kind of a weird title, I guess. And so it's all about kind of coming out of this canonical correlation analysis corner, which I'll explain to you what it is. And we'll go from there to common information. I'll try to explain to you this link for you to decide how convincing it is, but then we'll have kind of one firm theorem, which is, I guess, the fourth section, which says that for Gaussian, we can actually prove something strong. All right, so what does it look like, right? The setup is we have two data sets, the blue and the red one, the X's and the Y's, and they are kind of, aligned, if you wish. For every X sample, there is also a Y sample. And that is this numbering from 1 to little m, if you wish. Although we will not use this in the talk for real, not in this talk. And I guess one question that you can ask yourself is, around feature extraction or dimensionality reduction or data visualization, which is, well, if capital N, the length of each of these samples, and I've made it the same here, but that is actually not essential. It could, the Y's could be longer or shorter than the X's. It just makes the notation simpler. So let's take them to be of the same length, but let's suppose that capital N is quite large. So it will be a little hard to understand what's going on in this data. And then this natural question of dimensionality reduction is that you would like to reduce each sample to a very short description that's hopefully salient. For example, a one-dimensional thing, right? So that's what I've drawn here, if you wish. The U, the little u's, are these very, compact descriptions of the X samples, and the V's are very compact descriptions of the Y samples. One dimensional, let's suppose, then you can plot it like this graph on the right-hand side on this slide, where on the X-axis I have the U's, and on the Y-axis I have the corresponding V, and so every cross corresponds to one of the samples. And then, if you wish, in this small visualization, the idea would just be that from staring at this plot, you could infer something about what kind of data you're looking at, right? So that's this very high level picture to have in mind. It's a natural question, right? And it's a very old one. I guess what I found is these two kind of origins, it may go back further. And, some of you I know are interested in historical aspects of math, and I'll be curious to hear. But I guess here there's one work going back to Camille Jordan in 1875, and then perhaps more in the language that we like, by Harold Hotelling in 1936 about how you would do this. And what they did is a technique called canonical correlation analysis, which looks as follows, right? We look at the correlation coefficient between two random variables. I've just written this generic formula for you here again, but of course you all know this. So subtracting out the means and normalizing by the variances. And then the idea behind Jordan and Hotelling is simply to project. So you take your vectors, your long vectors x and y, and you project them, project the x vector into direction a1, and you project the y vector into direction b1. And now you pick, how do you pick a1 and b1? Well, the idea is you pick them such as to maximize the correlation between these two guys, okay? So that's a thing, and I'm sure that many of you have seen this, but I need some of it, so I want to go through it perhaps at slightly too much detail with advanced apologies. The device to analyze this is, not surprisingly, the covariance matrix of the merged vector xy. Here it is, right? So I've written it out in way too much detail for you here. That's I'm stacking x and y into one long vector. And apologies, this should be a capital N to be consistent with what I said before, but well, I think you get the picture here. So I've just got in this matrix all of the different covariances. And of course, there's 4 portions to it, and that's the bottom description here. There's a portion kx, which is the covariance matrix of x itself. And then there's ky, and then there's kxy, which is the covariance matrix between x and y. And CCA lives and dies because you can, without loss of generality, rewrite this covariance matrix into, or we should say by linear invertible transforms. That's actually the important thing. By linear invertible transforms, you can rewrite this covariance matrix into this very nice shape, right? Where you have these identity matrices here on the upper and lower, along the blocks of the diagonal, if you wish. And off of the diagonal, you have 2 more diagonal matrices, which I'm calling here capital sigma. So the claim is that you can get these new coordinates, so to speak, x twiddle and y twiddle, where x twiddle is just a times the old x and y twiddle is b times the old y. And these are invertible matrices. And you get to this very nice shape. Now, what's so nice about it? What do we like about it? Well, if you permute just a little bit the entries, right? I've done this here, so you can see between these 2 forms, all I do is I permute rows and columns, and you can see it is essentially just a block diagonal matrix where you have these 2 by 2 blocks. So what this transformation does is it takes the original random vectors x and y and it converts them into 2 new random vectors that are composed of uncorrelated pairs, right? So specifically in the tilde land, x tilde and y tilde first components are correlated with some correlation coefficient sigma 1. But they're uncorrelated with everything else. And that's what's nice about it. And so then, of course, maximizing the correlation now is very, very easy. In these new coordinates, you'll just pick the largest of the sigmas, right? And that's going to be your projection that you want to keep. That's going to be the one that maximizes this problem by Jordan or Hotelling later on. And perhaps just very, very briefly to see how you do this, right? What you do is to find these matrices A and B, these remappings. Well, you just start by whitening X and Y, meaning you divide by the square root of the spectrum with the usual. So if there's zeros, you don't do anything there and so on. But I don't think we want to go there today. Once you've whitened them, you get some kind of residual correlation between the whitened, so the x hat and the y hat. That's some matrix. And then all you do is you take an SVD of that matrix. And then you can see that the twiddled one, so the twiddle land, the one that we really like, is simply, multiplying the hats, the x hats, by the left and right singular vectors respectively. So that gives you this covariance structure. Not just this, and I'm sorry, I want to go quickly back here. What I should say is a very nice follow-up that's very natural in the land of canonical correlations is that once you got the most correlated one, right, you pick the one pair that has the highest correlation, you can then go down and pick the next highest correlation by restricting the new projections to be orthogonal to the ones that you picked in the first step. And in this way, you can build up, to the extent you want, at the resolution you like, you can build up these common parts, these most correlated aspects of these vectors x and y. And I guess we'll refer to this as the top k CCA components, right? Which now you just pick the first, k left singular values and the first k right singular values, and you project in the way that I show here on the slide. So this will be the thing that you want, the object of desire. K could just be 1, right? That was the picture that I had on the first slide, or it could be larger. All right.
Michael, a quick question.
Please.
Yeah, maybe it's a dumb question, but is there a relationship to PCA?
Yeah, if you wish, this is of course the same exact PCA concept. If you wish, the same as PCA, except PCA is about the single guy, right? And this is about two guys that need to be correlated. So it's in a sense is extending PCA to two guys, but it's right. It's about finding what's most correlated between the two guys. Okay. But it's definitely the same. Okay, let me put it this way. It's exactly the same logic as PCA. Yes. So that's definitely true. And I guess that said, right, PCA is also credited actually to the same paper by, or maybe not the same one, but to Harold Hotelling, right? He's considered to be one. I guess there's multiple sources of PCA, but that's one that is kind of,
So another question, Michael, that I got on the chat. So the question is there any relation to partial least regression?
That I couldn't say because I don't know what partial least regression is. List regression or least.
Least. So I don't know either, but maybe later on at the end.
So that would be for the end because I'd first have to learn what it is.
Sure.
Thanks for the question. So what does CCA do, right? So CCA, of course, has a very similar acronym to PCA, so this already kind of suggestive, but it means something different, right? It says canonical correlation. So anyway, how does it perform? Well, on Gaussian data, it performs as you would think it does, but here we're going to try to foil it, right? And it's a cheapo example reminiscent of the ones that you have done in your exams, you have asked or received in your exams, right? This binary modulo. So x1 and x2 are just binary. X is a vector of two components, but each component is binary and y is the same, right? And what you can see here is that the components x2 and y2 are just independent of everything and Bernoulli 1/2. And then the u and the v are correlated to each other, but marginally Bernoulli 1/2. And then, of course, that's the exercise you did. Any pair of these four random variables that sit inside the vector x and y is independent. So the covariance matrix of this is simply identity. So CCA doesn't do anything for this example, right? So in other words, it's a bit dissatisfying because there would be some correlation, there would be some dependence, let's say, between these two, but CCA fails to see it, okay? You can do the same exact examples for PCA. How can you do that? How can you fix it? Well, one fix, and that's not the one I want to go through, but I want to still mention it, is called maximal correlation. Also goes back to a long way, or Hirschfeld-Geberlein, where you say, well, let's not just do projections. Let's do functions. Any function f, any function g, well, measurable, but we don't want to go there today either. So maximize over all possible functions f and g. And I should say this does fix my binary modulo example, but in general, there is no nice solution for these functions. Perhaps not surprisingly, there's an algorithm that's somewhat interesting. It's called the ECE algorithm, alternating conditional expectation, but there's no closed form solution for this problem. And perhaps even more, and that's just a quick teaser for the very last part. What about having more than two data sets, right? I started out with just the red and the blue data sets. Suppose you also have a yellow data set, right? X, Y, and Z. I can set up another nice Bernoulli example in such a way that any pair of these three guys, so any pair x and y, x and z, y and z, are actually independent, right? And so anything based off of pairwise metrics will give nothing. That's clear because it's just independent. It will not find anything. And I guess what I'm trying to get at is that it's not really easy to extend from this correlation. How do you extend correlation to more than pairs? right? I guess there are some ideas, but they're not going to fix what I want to do. So instead, what do I want to do is a kind of a weird, different perspective on CCA. Okay, so you should shoot this down maybe at the end of the talk, but let me try. So CCA can also be understood as you first extract a common thing, a common thread, a commonality between X and Y, right? That's what I'm claiming. So I'm trying to explain this to you. So this is one way in which you can think of CCA. It first extracts a common thing, and that will be abstractly denoted for the rest of the talk by W, which is the projection of X into the best. So I'm using U here to denote the best direction, right? The most correlated one, and Y into the direction V. So these are the winners of the CCA game. That's the first step. You first find this, and then you project your data set X and Y onto this common thing W. What do I mean by that? In this case, it's a linear conditional expectation, if you wish, or the Wiener filter, or so you just do this kind of linear least squares estimate of W given X, right? And magically, lo and behold, what you find is if you do this on both of these components W, you actually get twice the same thing. In the case of X, you get U transpose X, comma U transpose X. And in the case of Y, also you get the same thing twice, namely what you want, right? So this is a way, seems like a bit of a roundabout way of understanding what CCA does, okay? Funny enough, and that's just a footnote, the same actually holds for max correlation. So in max correlation, so by the way, I should maybe say, if you want to prove this, it's just a bit of linear algebra. It's not, it's true only because U and V are the CCA achievers. Otherwise, of course, it's not true. The same thing turns out to be true for max correlation. You can now denote, you can say the common thing now is F star G star, okay? Right, that's the common thing. And then again, you project, this time it's really the conditional expectation, nothing linear, just the actual conditional expectation. And again, magically, it actually turns out to be the case that if you do these conditional expectations, you get twice the same, so to speak. It actually gives you F star for X and G star for Y. Again, to prove this last step, I guess it follows from what's called Rayleigh's representation of max correlation. It's not hard, but I don't want to prove it here. All right. So this is what we want to work on. So I guess the proposal is, in that case, if that's what it's doing, right, let's think a bit more fundamentally about what it means to extract a common thing between X and Y. So that brings me to my second topic, which is common information. All right. So and just to quickly motivate it with an example, let X and Y be these two random vectors. The X has a U, and in the first component, in the second component, just X2. And Y also has U and then Y2. And they're all independent, U, X2, and Y2. And in a sense, you know, you can say that anything that's common information, that calls itself common information, should answer its U, right? That's in a sense the idea. Now you can extend such an insight in many ways. In fact, one leads directly to mutual information. I'll let you figure this out. Another leads to Gauch-Kerner. I'll also let you figure this out. What I want to do is this here. So generalizing this insight as saying, search for a W such that X and Y are conditionally independent, right? That's true about U. If conditioned on U, X and Y are independent. And such that W is very compact, right? Because conditioned on U, comma, X2, comma, Y2, it's also true that X and Y are independent, but there's kind of fluff in there, unnecessary fluff. How should we measure compactness? What we'll do here, there's various ways again, and I challenge you to do other ones. We will do what Wiener proposed in 75, which is to measure compactness by the information, the mutual information between the pair X, Y, and this W that you keep. Right, so that's what we say. You want to minimize the information that you keep about the pair X, comma, Y, but you have to make sure that you're conditionally independent. So given W, you must be conditionally independent. So that's a slight, it's actually not such a nice optimization problem. The objective function is convex, but unfortunately the constraint set is not. So it's not so easy to solve. It's known, for example, for a binary symmetric double source. That's just to say that X and Y here are Bernoulli 1/2 and you know, connected by a bit flipping channel. I've plotted for you here a flip probability. We won't need this. What we'll need is the thing at the bottom of the slide. the optimizing W in this case can be described as W is equal to, well, let's say X, if X is equal to Y, right? And it's something completely independent of everything else, just a Bernoulli 1/2 if X is not equal to Y, right? That's what we're looking for. And maybe I should go to the previous slide. What you can see down here, that's what we do. We minimize over all possible W's that can depend in arbitrary ways on X and Y, okay? So this turns out to be the solution, not easy to prove. And in fact, there's a very special choice of alpha that I'm not writing on the slide because it's a pretty ugly formula that ensures that you are conditionally independent. So proving that this is the correct answer is not easy, but we won't need this. We'll only need the fact that this is the optimizer. The other thing that we'll want, and that's coming back to CCA. And maybe here I should quickly say for CCA, as I told you, there's this nice knob, right? You can say, I want 1 dimension, I want 2 dimensions, I want the 3-dimensional. You can choose how many important components you want. We want to bring in this knob. And the idea is to go with something that we'll refer to as relaxed Weiner's common information. And to motivate this here is a silly example. Perhaps we have X and Y are now composed of 3 pieces, right? A U that's common to both. And then this Vx, Vy, which has some kind of correlation, for example, like the doubly symmetric binary source that we just brought up. And then X3 and Y3, which are just independent of everything else. Right. And so the note that we'd like to have is that at the course level, it only tells you U, because U is really kind of the most significant common information. And then as you refine further, you want to get also whatever more there is between Vx and Vy. And the definition that we use, I should say it's not unique. I should say, you know, I challenge you to investigate others. The one we pick is this one here, where we say we introduce this knob gamma, which is that you don't have to be conditionally independent now, but your conditional mutual information cannot be too big, right? So conditional independence, if you stare at this formula at the bottom of the screen, would be if you pick gamma equal to 0, then the conditional mutual information is 0, it means conditionally independent. If you raise gamma a little bit, then you allow more and more distribution, so you can bring down the minimum if you wish. And you can play with this knob, okay? And I guess I have a picture. It's not particularly insightful, so I'm debating how much to say about it. I guess the idea here is on the x-axis, I have this gamma, this relaxation parameter. And on the y-axis, it's just the value of the common information, so how much there is. You can see that I have Weiner's common information as the highest intercept on the y-axis up here, and that's of course when gamma is equal to 0, because when gamma is equal to 0, we revert exactly to the original problem of Weiner's common information, and then otherwise it should go down. You can show a few nice lower bounds, but what you can also show is that here, for my example here, it's exactly just this straight line, and then it'll be some convex shape, I guess, bending upwards in that case, of course, ending at, you know, this Weiner's common information, the non-relaxed version. So the important takeaway point is not necessarily this figure, actually, it's really that we have this knob gamma by which you can kind of take more or less of the common information between the two guys. Then we have a whole bunch of properties. I don't want to go through them. Actually, I probably should not even show this horrible slide. If not, one property that I should point out, which is this red one in the middle, a tensorization property that we will need in just a minute, which says the following. If you look at the common information between strings of x's and a string of x's and a string of y, right? So that's x to the n right here, and oops, and y to the n. How do I get back? Maybe, how about this? And y to the n. Then here we go. There was a fun function. So the common information at resolution level gamma between these two strings can be written as, in this tensorized way, in a particular case, namely when these two strings, x to the n and y to the n, are made up of independent pairs, right? So each pair for a particular I, of course, xi and yi, they can be arbitrarily connected, but independent of everything else. And that's, of course, reminiscent of what we said at the very beginning, this coordinate transform, which gave you, in that case, uncorrelated pairs and in a sense we'll connect the dots, but I think you can already see where this is going. So this is a tensorization property that you can prove. It's a little ugly because of this minimum that you still have to execute. You have to spread this gamma budget, this relaxation budget over all of these n pairs, giving in a sense more to those that have really high correlation or dependence, and less where the dependence is smaller. I won't talk about the other ones, and instead say now, so what is our algorithm? I think it's what may be very clear, right? It's exactly along this line, the line of what I said, this interpretation of max correlation or CCA, which is, right, you first find a common thing and then you project. Well, strictly speaking, first you pick your resolution level in this problem. You have to first say, well, how many components do you want, so to speak? But in this case, it's just a real number. You pick your gamma. Picking gamma small means you get finer resolution. You get a lot of common information, really everything. And the larger you pick gamma, the more coarse your common information becomes. So large gamma corresponds to small k, small number of dimensions that you retain. And then the next step is just find this, Weiner's common information. And the last step is projected. I think at the very bottom of the slide, I have exactly this conditional expectation projection. In the paper, I have even a third one, which I don't want to talk about here. But another one that's also interesting is what I'll call this map projection, where you just the low dimensional version of X is nothing but the argmax of the conditional marginal, this P gamma of W given X overall W. So that's I guess another way in which you can project. And in a sense, this is a design problem. You can come up with yet other ways, I'm sure. And so this is the algorithm. So back to the binary model example, right? We had this one here. I explained it in some detail. And you remember that CCA does not do anything here, right? Because it's just identity covariance. CICA with gamma equals to 0 does exactly what you would like, right? Which is reduce X to W and reduce X to U, sorry, and Y to V, okay? I guess maybe just quickly to see this, right? The first observation is, of course, if you do a modular sum just locally of the vector X, then this irrelevant component X2 falls out, and we're left with just U. And then Y, the same thing, right? The irrelevant component Y2 falls out, just left with V. That's what I see right here. And then all we have to do is find this Weiner's common information problem. Now, if we assume that U and V are this binary symmetric source, as we did, right, for our example, then of course we stated that the solution takes this shape. The W is just equal to U with this famous bit flip alpha that I haven't told you. If U is equal to V and otherwise an independent Bernoulli 1/2. If you do a simple calculation to find the conditional marginal, you'll find that that's just a bit flipping channel with a bit flipping probability that's smaller than 1/2, and hence you find that you reduce X to U and Y to V. I don't want to say more about it. It's very straightforward. I just want to kind of go through it for once for real. And like I said, the main thing that's maybe closest to my heart is that one can prove that in the special case of Gaussian statistics, this CICA procedure, using whatever projection you want of the 2 or of the 3 that we have, in all cases, the CICA becomes exactly CCA for Gaussian statistics, right? So that's a kind of a sanity check that maybe this procedure is interesting, has some merit, right? We don't know, okay, but that's kind of the story that I'm trying to tell you here. So for the Gaussian case, we first need to understand how does this problem work out when X and Y are jointly Gaussian random variables. Just scalars for now, so they're the usual nice scalars with a correlation coefficient rho, and that actually has a very nice formula. So this is the formula for the relaxed Weiner's common information, jointly Gaussians with correlation rho. Yeah, maybe I should say this. Note that the variance of x and y have no impact, and that's intuitively very pleasing, right? That would be kind of similar to CCA, actually. The variance in the end doesn't matter because you're only after correlations. The other note is that this formula corresponds to the case when the auxiliary W is picked jointly Gaussian with x and y. That's very easy. Once you assume that W is jointly Gaussian with x and y, then it's a bit tedious, but you will get this formula. So the hard part of the proof is actually to understand that indeed it is an optimal solution. It's a minimizer to pick W jointly Gaussian with x and y. How did we do this? Well, I have a little picture here. Forgot. This is what it looks like. I guess it's a fun property about the slopes, which is very helpful in solving the allocation problem. But actually, I think I will not say too much about this, and instead tell you a little bit about the proof. So the proof, the core argument of the proof is this old theorem by Koch and Bernstein, which perhaps you have had in your probability class. I actually haven't. I hadn't. So I discovered it much later. It's not actually that hard to prove, but at least with characteristic functions, you can quickly prove it. It says the following: if you know of two random variables, x1 and x2, that they are independent, and you happen to know that x1 plus x2 and x1 minus 2 are also independent, then that is enough to infer that they are Gaussian. I should have written Gaussian because I call it Gaussian everywhere. Sorry about that. x1 and x2 are Gaussian random variables. Okay, so if you see in the if part, there is no mention of Gaussian anywhere, right? So the Gaussian really comes out of thin air, which is kind of nice. Now, the art of using this to your advantage is not something that I will explain here. Sometimes some people like to call it a doubling trick, or you look at two copies of the optimizer and you show that x1 plus x2 is also an optimizer by often an information theoretic argument. And it's not quite everything. We need something called the factorization of convex envelope, developed, I think, mostly by Geng and Nair and others. And perhaps just to put a small plug, a similar argument has been used by Geng and Nair for the broadcast channel and also by us for the M-user multiple access channel with feedback. So this argument has been used for a few things. There's more examples that I could have added. Has been used for a few examples. You can also use it nicely actually for classes. You can use it to prove max entropy and other things. So in quite a nice way. Okay, so that's kind of the heart of the argument. Now, what to do with Gaussian vectors? There's not much to say here. I've said most of it in my preparation on CCA. So now let x and y be jointly Gaussian random vectors, right? Same dimensions. Of course, that's just, I've rewritten the definition of my relaxed Weiner's common information with this budget gamma, right? So how do we proceed? Well, of course, we remember that one-to-one transforms do not change. Well, actually, I didn't go through this, but if you just stare at the formula, you can see that one-to-one transforms do not change relaxed Weiner's common information. Why is that? Because think about changing x and y. It shows up only inside information expressions. And there, it's very easy to prove that one-to-one transforms will not change the value of an information expression, if you wish, by data processing inequality. So we apply a one-to-one transform, and of course, it's going to be our favorite CCA transform. So instead of doing x and y, we do x tilde and y tilde. And if you wish, this last sentence is the key. As you remember, of course, the pairs right after doing this transform to x tilde and y tilde, the pairs are uncorrelated. But you also remember that for Gaussians, if you're uncorrelated, it means that you're independent, right? So CCA transform in the Gaussian case gives you independent pairs. And at that point, we can use our tensorization property. And we know that the Gaussian vector case has this simple formula with, I guess, the asterisk that you still have to do the allocation problem. It doesn't have a closed form solution. I have one picture here, right? You have to pick, if you like this parlance, a water level. So you pick a water level, and you can see these are the gammas here. And then this will tell you how much of each, how you pick each of these gamma i's, and then you can figure out the value, if you wish, of the relaxed Weiner's common information. I think what's yeah. Oh, and maybe I should emphasize this. What's nice is perhaps this, to realize that you can see that what is the K, which is the number of survivors in this little game here, right? What you can see is in my picture, the n minus first and the nth component, the ones with the smallest correlation in this particular configuration, do not get anything active, so they will be at 0. Their contribution will be 0, right? So that's the meaning here. And so K is the number of survivors, or let's define K as the number of survivors. And you can see, I've done it out for you here, but it's from the picture quite clear, is that if you pick a really small value of gamma, then everybody survives. And if you pick larger and larger, then you will have only the most important, only the coarsest guys are left. Maybe I should show you the K of gamma function. And so here's the theorem. I haven't written it as a theorem, but this is kind of the main result, right? It says that, let's first look at the left side. So for a random vector with covariance matrices, and here I'm just writing these entries, right? Kx, Ky, and then the covariance between x and y. We saw that the CCA logic is find the top k CCA components, right? That's what you want to do. For example, the top one, then you just project on the most important right and left singular value. On the right-hand side, this is what CICA does. For Gaussian random vectors, it first solves the relaxed Weiner's common information problem, right? At some level gamma, and I guess we know in the Gaussian case, we know exactly how to translate a certain gamma into the K that you will get. Then find the optimal auxiliary. I guess the optimal auxiliary can be shown. I haven't shown you exactly the full proof for this, but because it's jointly Gaussian, I guess it's quite believable, can be shown to take exactly this shape, right? It's the sum of the X parts, the Y parts, and well, some additional Gaussian noise. And now, I guess I've written it here only for the conditional expectation. It will be the same for the max probability. So now just find these conditional expectations. And if you do that diligently, you'll find that it's exactly the same thing as over here. There is, I left it in here, there is, if you actually do the calculation, you'll see there is this nuisance by just a diagonal scaling matrix. But that doesn't matter because the CCA problem is only defined up to scaling, right? You can always scale up and down. And I guess one common normalization of CCA is that you say the vectors have to have a unit norm. So this is, in a sense, this is the whole proof of this main theorem. I haven't shown you the full details, but you get exactly the same answer for in the Gaussian case. All right. And so I think the most interesting part in many ways, and I don't have full answers there, is what I'll call the multivariate case. So what if you have more than two, right? We mentioned, so for two, the goal was to extract u of x and v of y to capture the commonality, okay? What if we have x, y, and z? And actually, let me number them because I'll directly want to go to more than just three. So from now on, the data sets will not be called x, y, z, but x1, x2, x3. And we want to extract features u1 of x1 and so on, okay, representing the commonality. And that was kind of this, this early teaser that I said that seems unclear how you would do that for CCA. Here, of course, this rationale still works, right? You can still try to talk about what is a good definition of a common information or a common part between more than two, and the projection operation anyway is still well defined. But how should you define the common information? Right, for two, it was this, okay? For two, it was just the information that the W keeps, you want to minimize the information that the W keeps about the pair X, Y under the condition that W has to make X and Y conditional independent. And then we relax this conditional independence by a gamma. Right, so how to extend this to more than two? I think it's quite obvious for the first guy, right? Because here we can just say we want to minimize the information that the W keeps about everybody. And not just the two guys, but everybody. It's not so clear for this second part. Okay, the one that we've studied so far is one that uses what's called the total correlation. So this is the definition that we want to use. Relaxed wires information for m variables. We can define as this minimum. And now we have this new constraint here. It's definitely consistent when you pick gamma equals to 0. It says exactly that the x's have to be conditionally independent given w. When you increase gamma, what is its meaning? Well, I should say as a footnote for those of you who have studied this extension would be well motivated through the Gray-Weiner source coding network. So it would directly come, if you analyze that network, you would directly end up with this kind of a definition. But beyond that, you could definitely replace this by dual total correlation, right, from Tesvenhan's definition, or something else. We want to do just this for today, because for this actually we have some small result. So the algorithm is the same as before, right? Pick a gamma in the interesting range, that's your resolution level, solve this optimization problem leading to this, the distribution, and then you can again do this, map version or conditional expectation. You can see there's really no change. It looks exactly the same because it was not sensitive to 2. So what does this give you, right? We mentioned this simple 3-source example in the binary case, where, I guess, just to repeat quickly, u and v and x1 and y2 and z2 are all independent Bernoulli 1/2 random variables, okay? So you can see, and that's what we observed before, is that any pair of these vectors are actually pairwise independent, right? So there's not much you can gain from anything here. It seems, at least with pairwise measures. So but what would you like the answer to be? Let me put it this way. What would you like the answer to be? And I would claim one answer that you would be happy with is to reduce x just to u, y just to v, and z to u plus v, right? So if you think of kind of a 3-dimensional plot, that would, I guess, somehow capture the residual dependence, or if you wanted to visualize this data, I would show you the right thing. And we can actually do that. So it's not completely trivial. You can find the proof in the paper. You can prove, at least for gamma equals to 0. So that's just the classical, conditional independent case. We can show that the optimizing w in this, extended problem is exactly u comma v. And then if you project this back, you can conclude that that's actually the answer you'll get. You'll get exactly that, you project x to u, y to v, and z to u plus v. And I think, that's maybe more just an example to show you that, it could be a nice way of doing business. I think that's all I wanted to say. So we've introduced this relaxed wires kind of information and this algorithm. The main technical result is really this, right? Gaussian CICA equals CCA. I should quickly point out this, that the same technique actually also resolves the Gaussian Gray-Weiner network, if this is something that you're interested in. And that's described in the paper. I guess CICA can be applied to discrete value data in a meaningful way. That's a bit of a claim, right? I've shown you just some examples. Well, naturally extend to more than 2. And I think the big elephant in my room, of course, is how to practically implement this. So we're working on it. We have some, gradient descent style implementations. I don't have any impressive data to show right now, hopefully in the near future. So that's all I wanted to say, but I'm happy to discuss questions or anything.
Yeah, thanks a lot, Michael. So we can take questions over chat if people have questions. Maybe we can ask Zonghong to prepare to ask the question. I can try to unmute him because he asked the question about the least linear square. But in the meantime, maybe I can ask a question. So, what was your motivation in studying CCA in terms of applications? And do you think this new relaxed definition could also be applied there?
To what? Sorry?
So usually, what are the application of the original definition of CCA? And do you think this new definition with this gamma parameter could also help there? Like, I mean, in summary, what kind of application you have in mind for these definitions?
Oh, I see, I see. Well, like you say, right, the same exact ones that CCA had, right? CCA, you could say, in the first place, let's just call it data visualization, right? What would you do if you have exactly this situation? So you have collected data and it comes in pairs, right? One long vector X and one long vector Y, right? And you get many of these pairs, right? I don't know, some sensor network data or biological data or healthcare data or like, you know, society data or whatnot, right? So you would like to understand, you know, what's in this data, right? And I guess CCA is one natural way to kind of, you know, get started. You think like, well, you know, are these vectors close to independent, or like the, you know, is X kind of independent of Y, or are they quite correlated? Well, what you would do is find exactly, you know, the direction for each, the direction in which, such that they're most correlated, right? To pull out the common driver between X and Y. If there's none, right? If you maximize the correlation and you find it's just a completely round blob, probably there is nothing, right? Your X and Y are just independent. Instead, maybe you get, you know, blobs sprinkled across, or you get some high correlation value, right? Some kind of line, then you do something else. I think these are kind of the motivations behind CCA, right? Okay. And so it would be just the same. You could just use this CICA. If you know, if you, I guess, you know, at the very high level, my point is, of course, a bit mean, but it's to say that CCA is not such a good fit for discrete valued data, right? An extreme case of discrete valued data is this very meanly constructed binary symmetric example where CCA even completely fails. It doesn't do anything, right? So that's kind of the story is pick exactly an application where you would have done CCA. Your CCA seems to say there's nothing in the data. Well, try CICA. There may be something, you know, whatever, higher order, so to speak, right? There may be correlation, something that you cannot see just in correlations. It only shows up if you do a little more work.
Okay. So another quick question before we ask the audience. So in terms of the case where you have multiple vectors, how bad or good is the idea of stacking maybe two vectors together and then just reverting back to the case of two vectors?
Yeah, exactly. And that is a technique that people have tried, of course. That's exactly true. So if you look on your favorite resource, you know, Wikipedia or something, I bet you that's what they'll tell you there, that you try it in all possible ways. You just optimize, you know, one guy given everything else in this linear perspective. You can do that, right?
Okay.
So
among the audience, Emra has a question. So Emra, I think Christy will unmute you and you can ask the question. So let's hope this would work.
Can you hear me?
Yes, we can hear you.
Okay. So first, I want to thank you. It was a great, really nice talk. What I wanted to ask is, why do we need the relaxed variation of common information? Because tensorization works also for the classical, you know, I can specialize gamma to 0 and I get the classical common information, and all this nice, you know, CCA analysis would work for the classical common information as well. So I was wondering, is there a specific reason where, for example, is there a problem where we have to optimize over gamma so that the gamma wouldn't correspond to 0? I was just wondering about that.
Thank you very much for this question. I think this is, I'll try to modify slightly. So the thing, if you just leave gamma at 0, right, then in the Gaussian case, for example, you can immediately see what happens. If you fix gamma to be 0, then it's just a one-to-one transform, right? So you're not actually extracting anything, right? You're just transforming. So if you want to have this, you know, dimensionality reduction business, you need to say by how much you reduce, right? So, of course, in the Gaussian case, you're going to tell me always, well, it's always kind of, you know, dimensions. So we can just, but think about for, you know, an arbitrary, you know, discrete case or just any data, right? It would not be clear how you would reduce, right? There's no way, if you leave gamma at 0, that's always the most extreme case. You keep everything, right? You keep in CCA parlance, gamma equals to 0 is the same as picking k to be n, right? Meaning I dimension reduce the original vectors of length n to new vectors of length n, right? And you can see that's kind of not very interesting because it's still the same number of vectors, right? Now in CCA, of course, it's kind of easy. Once you have these n new vectors, you're just going to keep the first one. But you can imagine that if you have discrete value data, it's not clear what you would do next, right? There is no such nice ordering. It's not that it's just a matrix, right? It's some arbitrary remapping. It's not clear how you would do it. So in a sense, this gamma is key. It's super important. You definitely don't want to pick it in general. You don't want to pick it 0. The doctored examples, and that's maybe the mistake of my doctored examples. The doctored examples always had gamma equals to 0 because I set it up such that other than the gamma equals to 0, right, other than the common part, everything else was independent. But from the Gaussian case, you can see that if you wanted to use this in practice, you really want gamma, and you don't want to pick it just 0. In general, you want to play with gamma because some gamma will give you exactly the right level of resolution, right? The right coarseness, the right number of dimensions. It's a good point. I like it. I should think of a good example that really drives home this point. But if you think about it a little bit, without the gamma, it actually makes, you don't have an algorithm, right? Without the gamma, it's just, yeah, you can find this common information, but that's it, right? Then you cannot pick the number of dimensions. Does this make sense a little bit, or, well, a bit confusing? So, yeah, I'll work on it.
Yes. It makes sense. In the multidimensional case where you need the CCA, obviously, you would need gamma or something like that. Something that would eliminate the less important components. Thank you.
Thanks. So, Michael, we have one more question from Zonghong. So, if Zonghong could be unmuted.
Yeah. Sorry for my previous typo. I meant to ask about the partial least square question, and I just got the answer from some book. It seems that partial least square is just the y is one dimension. And I have another question. You have showed an example in part 2 of your presentation, which is x and y. They are both 3-dimensional random variables, say u, x, v, and xy. I think the gamma here is just mutual information between vx and vy, right?
Very good. That's a very nice observation. I did not take the time to explain this figure because I don't know, I just felt going through that the value was not big enough, but I'm happy to pull it up again. And you can see it here, right? You can see I put these labels in with the mutual informations and so on. Is that what you're referring to?
Yeah.
So if you wish, for example, this gamma, the most extreme value, this is the same as the mutual information between x and y, right? Because the x3 and y3 are independent, so that's all that's left. That's exactly the mutual information, as you say. And then I guess there's another interesting intercept when gamma is exactly equal to the mutual information between vx and vy. At that point, you start kind of bringing in the commonality between vx, right? If gamma is in this window, then it's only u. It's only going to be u. And then after here, you're going to start to bring in vx and vy. I don't know if that's related to what you're pointing out.
And in application, how do we choose gamma?
Very good. And there is really not a good answer to this, right? I don't know, right? I know it for the Gaussian case. I can show you exactly how you pick it, but more generally, I don't know, right? It's something that I think that's totally missing. I mean, we have this upper bound. Don't pick it larger than the mutual information because after that it's just nothing, right? You retain w is the all zeros random variable, but below it. It's a good point. And I don't know. I don't have a good answer to this.
I see. Okay, thank you.
Yeah, thanks, Zonghong. So next, Anand has a question. So Anand, you can go ahead and ask Michael.
Okay, hi. I had a question sort of about, maybe it's predictable. What if you have some uncertainty about the distributions of x and y, so I can see that, like, for example, if there's some parameter uncertainty in the Gaussian case, then your W sort of varies smoothly with the uncertainty that you have in, like, perturbations in say the mean and variance of the X and Y, or I guess maybe the mean, or even sorry, perturbations in the distribution. But do you have like a general result? Do you have like sort of a general sense that the W varies smoothly in some sense with smooth changes in the distributions of X and Y?
It's very, very interesting. I'm teaching this advanced information theory class, just whatever, randomly, and I came across exactly this question, asking myself, to what extent could one prove this, right? Because you can kind of construct in mean ways example, right? Because it just go back to gamma equals to 0 case, right? So now it's conditional independence. That's a kind of a brittle set, right? It's definitely not a convex set, because a convex combination of conditional independence will not be conditional independent necessarily. So you can quickly end up outside of that set by small modifications. That's what I'm trying to say. So I don't know right now. I don't know.
With the gamma, you're saying with, I guess the question is with gamma non-zero, are you getting also some smoothness, or like,
in the W, right? That's what they're asking about the optimizing, because as a function of gamma, that one can show, right? And I think I had it here on somewhere, right? You can show that this property number 3, you can prove that C gamma is a convex and continuous function of gamma. So of gamma, it's okay.
Right, but not of the distributions of X and Y necessarily.
Exactly. The distribution, exactly. Very good. So if you change X and Y, I think the W could change quite a bit. So
I wonder if you could do like perturbation analysis where you, in the continuous case, where you add a little Gaussian noise to X and add a little Gaussian noise to Y, but with very small sigma, and then see what happens.
Yeah, exactly. One would have to do stuff like that. Yeah, it gets immediate. I think one of the uglinesses of wireless counting information is that there's only a very, very, very tiny set of cases for which the answer is known, right? So you're quickly kind of just outside of anything, and you can do some, of course, some epsilon delta style analysis. I tried a little. I'm not there yet, but I think something can be said, but I don't know how much. It's a good question.
All right, so if there is any more questions, so we can take one more question. Otherwise, if no one posts anything on the chat, so we can conclude the talk. Michael, this is really nice. We really enjoyed the talk. So, and thank you again.
Well, thanks for the invitation. It was my pleasure. Back to the birthday party of my 6-year-old.
Oh, okay, yeah, sorry about
well, that was all planned later on. That's the thing of home office. EPFL is closed. I'm not allowed to go. So.
Great. Thank you, everyone.
Thank you.
Bye-bye.
All the best.